When a bullet strikes a standard pane of security glass at hundreds of meters per second, the result is immediate, explosive destruction. We routinely call materials designed to survive this kind of impact bulletproof, but in engineering, that term is a myth. The glass is not immune to damage. It is explicitly designed to break the moment a projectile hits it. The accurate industry term is bullet-resistant glass. Its ability to stop a threat is a strict mathematical function, weighing the glass's thickness against the mass and velocity of a specific ammunition caliber. But this creates an obvious paradox. If the material is supposed to shatter, how does a broken window successfully prevent a deadly, high-velocity projectile from passing right through? Stopping a bullet requires letting go of the idea of an unbreakable wall. The goal is to manage, redirect, and exhaust extreme kinetic energy. To see how this happens, we must freeze the action at the exact millisecond of impact. This 3D cross-section reveals that the pane isn't a single solid block. It is a composite sandwich made of alternating layers. We have thick outer layers made of standard hard glass, separated by thin, flexible sheets of a transparent plastic called polycarbonate. In the first phase of the strike, the projectile makes contact with that hard outer glass. By design, this glass is physically harder than the copper and lead making up the bullet. When the tip of the bullet hits that superior hardness, it instantly flattens out and crushes against the surface, taking on a wide, mushroom-like shape. Simultaneously, the hard glass cracks. Those fractures radiate outward, acting as a dispersal mechanism that spreads the bullet's intense, focused impact energy across the wide surface area of the pane. The hard glass is not meant to catch the bullet. Its job is to deform the projectile and dilute its kinetic energy through deliberate structural failure. Pushing past that shattered outer layer, the now deformed, slower-moving bullet enters the deeper sections of the composite structure. This is where the polycarbonate layer takes over. As the flattened bullet makes direct contact with the inner plastic, the material curves and bows inward instead of snapping. Unlike the rigid glass, it stretches under intense pressure, enveloping the projectile until its forward momentum drops to zero. By stretching, the plastic physically absorbs the final, diminished kinetic energy of the round, trapping it entirely within the layers of the sandwich. Because the bullet now has a much wider surface area from hitting the hard glass, it cannot pierce through the stretching plastic, keeping the safe zone behind the window completely secure. The system works in tandem. The hard glass diffuses energy by breaking, and the flexible plastic absorbs what remains by bending, turning a lethal projectile into a trapped, harmless mass of metal. Returning to real time, the aftermath of the strike leaves the bullet permanently lodged inside a heavily damaged, unusable pane of glass. Yet, despite the extreme destruction visible on the strike face, the innermost layer, pointing toward the human occupants, remains smooth, intact, and structurally uncompromised. Relying on blunt, rigid strength is the wrong approach to stopping ballistic threats. Completely unyielding materials transfer force straight through to the other side, rather than absorbing it. This dual-action mechanism of cracking glass and stretching plastic relies on a calculated engineering principle known as sacrificial design. Sacrificial design is the intentional destruction of a material in order to safely dissipate lethal amounts of kinetic energy. Ordinary glass fails completely and dangerously under stress, shattering into hazardous shards. This engineered composite fails constructively to serve a very specific purpose. Bullet-resistant glass saves lives by offering itself up for controlled destruction. It proves that sometimes sacrificing the material is the ultimate defense.